Multi-layer network. This tool helps you understand how a multi-layer neural network is trained and used to perform predictions. A multi-layer neural network is an advanced model used in artificial intelligence and machine learning. Imagine it as a collection of interconnected perceptrons, the topic we talked about in a previous session. However, unlike the perceptron, which only has one layer of neurons, the multi-layer neural network consists of multiple layers stacked on top of each other. Each layer receives input from the previous layer and applies a mathematical operation called an activation function, just like the sigmoid function. This allows the network to capture complex relationships between inputs and outputs. To make the network learn, we use back-propagation, a technique that adjusts the weights connecting the neurons based on the error between the predicted and actual output. This adjustment is guided by gradient descent or other algorithms. Through this iterative process, the network improves its ability to make accurate predictions, ultimately enabling it to solve complex problems. This tool will help you understand how a multi-layer neural network is trained and used to perform predictions. Let's explore it. Here are a couple of examples of neural network training and predictions: the height-weight example and the exclusive OR example. Both examples have two inputs and one output. Let's keep it as the height-weight example as the selected one. Below, we have a dataset for the selected example as x1, x2, and the target t values. Next, we have some buttons to start or stop and reset the training. The rate at which the values on this image are updated can be controlled with this slider. The default value is 10 epochs, which means that the values in the graph are updated every 10 cycles of forward and backward propagation. Next, we show the neural network model and its weights, biases, and intermediate values. The values will be shown once the training is started. This particular neural network model has two layers: a hidden layer consisting of two neurons and an output layer consisting of one neuron. Each neuron receives the input from its previous layer, or input layer. It performs the weighted sum and passes the sum through an activation function. The weights are represented as W1 through W6. The neurons also take biases B1, B2, and B3 as inputs. The weighted sum of each connection is shown here as H1, H2, and Y, followed by the activation function output, which is shown as AH1, AH2, and AY. The computed output and the target output are shown here along with the loss value. Finally, we have the prediction section. Once the network is trained, we predict the output by providing input values and pressing the predict button. Let's select the exclusive OR example from the top. So let's press that. And let's press the start button and stop it immediately to see the results after a few iterations or epochs. The network is paused at the last input of 1 and 1. So let's explore some values. Here we have input x1 and input x2. These are the weights W1 through W4, which are in play for the first layer. These are the two bias values B1 and B2. The first neuron of the first layer performs the weighted sum as x1 times W1 plus x2 times W2 plus B1, which results in this value H1. This value is then fed into the sigmoid function as shown as AH1. Similarly, here below, H2 is calculated using x1, W3, x2, W4, and B2, and it's displayed here. the sigmoid function is applied and shown as AH2. Next, these two outputs are fed into the next layer, which is an output layer, and the weighted sum is computed as Y. And it uses weights W5, W6, and bias B3. Again, the sigmoid function is applied and the output AY is calculated. Finally, the loss is calculated between the mean square error between points AY and the target T. Let's run some more iterations until the loss is reduced down to about 0.02. Notice how the weights and biases change with the number of epochs. So let's keep waiting until we reach our desired loss of 0.02. There we go. We have loss of 0.021. We can stop it now. Note that after 1,160 epochs, the loss has decreased to 0.021. Now let's do some predictions. If we put 0 and 0 as the input, we expect the output to be close to 0. So we can press this predict button, and we see that the result is not completely accurate as desired, but it's good enough for learning and illustration purposes. For more accurate models and in real applications, we use more layers and more neurons per layer. Let's try some more predictions, such as input 0, 1, and we get that the predicted output is 0.791. For 1, 0, we get the predicted value as 0.880. And finally, for 1, 1, the output or predicted output is 0.109. Not bad for a simple network like this. From here, you can continue training with the start-stop button or reset to the initial state with this reset button and explore the values at any state. This covers how a multi-layer neural network works for a simple example like exclusive OR. Similarly, we can try the height-weight example by selecting it from here. In this example, the system classifies a person's gender based on their relative weight and height. The input in this example is x1 as relative weight from an average human weight, x2 as relative height, again from an average human height, and the output t, which is 1 for a female and 0 for a male. Now we can start using this data set by pressing the start button and the same two-layer network for training and prediction. We can try some predictions like the other example. For a relative height of 20 and relative weight of 2, the predicted gender is 0, which means it's a male. This covers how this tool can be used to understand a multi-layer neural network. Please feel free to play with this tool by trying different examples, data sets, and running the simulation with any number of epochs and graphics update rates.